Logic Design, Chapter 2, Lecture 3. So far, in the first introductory lecture, we have seen and we have introduced the binary numbers and we know how the binary numbers are working. And we have seen how from a different bases like base 10, base 8, and base 16, we can convert to binaries and vice versa. And we also have seen how we can do arithmetic operations using binary numbers, addition, subtraction, multiplication, and division. And then we have also seen how we can use complements. Instead of doing a subtraction, we can do complements and addition. So we can have we can use less resources and it will be more efficient. And then we have introduced different coding techniques, including binary coded decimal, which is one of the important ones. And by using binary coded decimals, we can do arithmetic operations as well. And we have seen the sign by BCDs as well. And we also introduced gray codes, XS3, and ASCII codes, which are different coding techniques as well. And in the last part of chapter 1, we have seen how digital logic or the binary numbers are kept in a digital or a physical device by using registers and by seeing a register transfer operations. Then one of the most important thing in this course where we are going to use the logic gates, we have introduced the basic logic gates AND, OR, and invert. Now, taking from there, in this chapter, we are going to build up our knowledge and we are going to introduce how these functions or gates are going to be combined into different functions that we can use to express a logic operation or a logic device. And in order to do that, we have to understand algebra. So what is algebra and how do we use algebra is something that we already know in the high school. And we are going to apply that algebra knowledge into binary numbers in this chapter. So let's start with the basic definition. So algebra, it's a mathematical system, as you all know, where we can have set of elements A, B, C, D, W, X, Y, Z. We can have set of operators, addition, subtraction, multiplication, and we also have some axioms or postulates, or let's say rules or laws that we can do this operation or we cannot do this. So generally, why algebra is really important is it actually defines the rules and the laws of the calculation. Okay, so first, I want to give you a brief overview of a revision of the algebraic postulates and the theorems that we generally use. And then we will apply these and we are going to find the relationship between these and the binary version of algebra. So when we talk about basic definitions, the first thing that we consider is a set. Set is a collection of having same property. We all know that. So X and Y can be an element of a set, and S can be 1, 2, 3, 4. So if X is equals 2, that means X is an element of S. If Y is 5, that means Y is not an element of S. So when we talk about these, we can also introduce a binary operator. When we say binary operator, it's not actually zeros and ones over here. Binary operator, so based on the set elements, when we do some operations, and if the result of that operation is also an element of that set, we can say that it's a binary operator. Okay, so for example, for a given set S, we have got X star Y. I'm not saying multiplication, it's X star Y, which equals Z. So star in this case is a binary operator. How if X and Y, which are elements of S, when we use a star operation and we get the Z, which is also an element of S, then we can say that star is a binary operator. Then if star is not a binary operator, that means the result that we are going to get is not going to be element of that set. So the basic first rule in the ordinary algebra is the closure law. So what is closure law? If we talk about it, let's say we have got a set which we have got natural numbers 1, 2, 3, 4, and so on. Okay, now closure is coming from a point. Let's say I want to do a add operation. Okay, simple arithmetic. Now if I add 1 plus 2, okay, if this is a binary operator, if I add 1 plus 2, I'll get 3, which is also element of that set. Natural numbers can go from any positive number to infinity. Okay, so that means add is a binary operator. And we can say that the result is 3, which is element of that set. The closure law applies. So closure law validates. But if you think about it this way, 1 minus 2, if I use binary operator minus, then I'm going to get minus 1. Now, minus 1 is not an element of these natural numbers. Okay, so minus 1 is not an element of n. So in this case, not closure law. So, okay, so no closure. That means the set is not closure. Or if you are using minus operation, that means it's not a binary operator. Now, another law that we generally use in ordinary algebra is associative law. So associative law is x star y star z, either these in parentheses or these in parentheses, it doesn't matter. You are going to get the same result out, where all elements x, y, z are element of S. Okay, so you can try this with addition, x plus y plus z, or x plus parentheses y plus z will give you the same answer. Even if you are doing multiplication, that's also valid. And commutative law, similar to it, either you change the positions of your elements, x star y or y star x, it will always going to give you the same result. That's what commutative law is. And identity element. So identity element is when you consider, for example, addition. When you add something to that value, it's not going to change its value. That is 0 in addition. And in multiplication, when you multiply something by 1, you are going to get that same result. So x dot 1, x multiplied by 1, it's going to be x. Or x plus 0, it's going to be x. So that is identity element. So I'm guessing you all know these basically from the ordinary algebra. Inverse is just inverse of it. So if you have x, the plus x, then the inverse of it minus x. Or if you have x dot something, that's going to be 1 over x, for example, multiplication and division. So we have got the inverse of those, and they have to be element of that set as well. And another important definition or law is the distribution. So when we want to distribute, we can do x star y dot z. Okay, so that will be x star y, x star z. We can do that. So we can say that we can distribute it over. Now, these are some important laws that we use in ordinary algebra. Now, when we think about it as arithmetic operations like addition, subtraction, and so on, we can relate these two into these couple of definitions for the real numbers. Now, when we are talking ordinary algebra, the binary operator plus, it always defines the addition, and the additive identity is 0, so x plus 0 will give you 0, and additive inverse of it is subtraction. So plus 3 minus 3 will give you 0 as an inverse. Now, binary operator dot defines multiplication, or you can just say star or cross. Multiplicative identity is 1. X dot 1 will give you x. And inverse of that is 1 over x. And the only distribution that we can apply in ordinary algebra and real numbers is dot over plus. So we cannot have plus over dot. We can just distribute it x dot y plus x dot z. We cannot do other way around. Okay, so these are some of the important definitions that we are going to use and apply to it. Now, when we think about it, binary numbers, we have got some properties over there which we can use it for algebra, or we can have some laws which in algebra that we can apply to binary numbers, and that's what we are going to see next. So Boolean expression is made up of binary variables, x, y, a, b, data, clock. These are all input variables, and constants, zeros and ones, and logic operations, or and invert, XOR, which we are going to see later, and parentheses. So in this case, for example, we can use input A, B, C, and we can write an expression using algebra. This is known as Boolean algebra, which we apply to binary numbers. So in this case, we can say that A, B, C are the input binary variables. They can take any value from 0 and 1. And Y is the output variable. Based on the operation, we can have some output. So this is going to be like C and, in parentheses, A or 1 or A dot B prime. Okay, so this is an expression that we can apply or use to it. Now let's see these properties of Boolean algebra. Now, this is defined by the George Boole in 1854, and then it's expanded with the Huntington postulates in 1904. Okay, and binary set, we already have two variables in there, zeros and ones, okay, the values as it is, and two binary operations, mainly and or operations. So when we consider arithmetic, binary arithmetic and ordinary algebra, we can apply some of those laws, like, for example, closure with respect to operator, or and AND. What do we mean by that? Let's say we have a set of binaries, which we have just got 0 and 1 inside. Now, is it closure? So 1 or 0 will give you 1. 0 or 1 will give you 1. 1.0 will give you 0. 0.1 will give you 0. 1 or 1 will give you 1. 0 or 0 will give you 0. 1.1 will give you 1. And 0.0 will give you 0. Now, when you think about these outputs, they are all element of that binary set, as you can see. So we can say that closure law can apply. So the set B, which is a binary set, is closure with respect to AND operation and OR operation, and we are always going to get the values 0 and 1. Identity element, it's the same as the ordinary arithmetic. So 0.0, it will be 0. 0.1, it will be 0. Okay? So as you can see, this is always getting 0. So in AND operation, we cannot say that we have got 0 as a identity element. But if you think about it, 1.0, that will be 0. 1.1, that will be 1. So no matter what this is, it's always going to be getting the same values. Okay, so for AND operation, it's 0, and for OR operation, so 0 plus 0 or 1, it's going to be 1. 1 or 0, it's always going to be 1. Or 0, it's going to be 0. Okay, so 0 in this case is an identity element for OR operation. When we consider commutativity, x or y equals y or x. So 1 or 0 or 1, it's always going to give you 1. Or 0 or 0, 0 or 0, it's always going to give you 0, and they are same. So commutativity also applies. Distributivity. Now, we can distribute in any way in Boolean algebra. In ordinal algebra, we have to distribute dot over plus, but in Boolean algebra, this is important, we can distribute in both ways. So x dot y plus z can be distributed as xy plus xz, or it can be other way around, x plus y dot z can be distributed as x plus y, x plus z. So it can be distributed in both ways. Complement x, complement is x prime, inverse of it. Or let's say x plus x prime will always give you 1, and x dot x prime will always give you 0. So 1 or 0 is 1, 0, 1 or 1 and 0 will always give you 0. Okay, so these are the complements for every element. And in Boolean algebra, we always have two elements, x and y, and they are never going to be equal to each other. So this is like 1 not equals to 0. Now, terminology, the literal is a variable or its complement, x, x prime. Product term, literals connected by AND function, x dot y, y dot z, a dot b. Sum term, a plus b, x plus y. These are all sum terms that we generally use. So when we consider the gates that we have seen at the end of chapter 1, AND gate, OR gate, and NOT gate, if you do remember the truth tables for AND gate, when both inputs are 1, output is 1. OR gate, if either of the inputs are 1, output is 1. And NOT gate is just the inverse operation of it. So set B is always 0 and 1, and two binary operators AND OR, and the rules of operation, we can also have invert in there. And if we summarize it, closure law, 1 and 0 are both elements of B. Identity law, 0 for OR operation and 1 for AND operations. Commutativity, both ways, x plus y, y plus x, or x dot y, y dot x. Distributive law, either way we can distribute it, and complements x plus x prime is 1, or 0 plus 0 prime is also 1. And same applies for the AND operations. And we have got two distinct elements. So set of two elements, plus is representing OR operation and dot is representing AND operation. A complement operator is a NOT operation, and it is a two-valued Boolean expressions. Now, we have got some principles that we are going to see next.